Okay, so let's start with Lemma 1.2. First, we'll give some definitions. Um, so the first definition is f is accessible mod some set x if okay, so I will say that a point x goes to y if there exists a US path joining x and y. So it's accessible if for every p and q, so we have a finite number of points on the set x, and such that we can join p to x1 by an US path, and x1 to x2, and so on until xr, and then we join with q. We say that it is the accessibility is uniform if so there exists some number n such that the number of legs on this sequence of paths is less than n, and the length of those each one of these has a length that's less than n also. Okay. Okay, so another definition is about the function r. So r of a set x is the minimum of the j's such that so we do not have intersection and until j. So an intersection occurs on j plus 1, something like this. Could be infinite. Okay. And so for me, so the D will be center disks. I will use the notation of the paper. So it's is a center disk with center on P and radius rho. And so beta D will be the same disk, but you multiply the radius by beta. Oops. What? Yeah. Okay. And A will be a family of finite central disks, and okay, so beta A will be the same disks but multiplied by beta. The norm of A will be the union of the disks on A. The radius of A will be the maximum of the radius of each disk, and R, capital R of A, so the recurrence of A, it will be the function R applied on the union of the disk. Okay. So these are the definition, the basic definitions, and lemma. So the lemma 1.2 is so given f partially hyperbolic blah blah blah, which is Kupke's Mail. So in particular, for each period, we have finite number of periodic points of such period, and then for every j, we have a collection of disks such that they are small disks. The recurrence of the disks is very large. So and what we have is that f is uniformly accessible mod 1/2 of the disk. Well, these numbers are anyway not important, but okay. So this is the main lemma 1.2, and let's start the proof. So the idea, well, the main idea is that the first we obtain this recurrence away from periodic points, and this is why this hypothesis is needed. Okay, so how we do, so let's call x1 to xm, like the periodic points with period less than j, and then we get we set a like the manifold without this finite number of points as a connected set, and the first lemma, so lemma 2.1, so says the following. So says that, okay, so if you take r very small, okay, and then so you consider AR like the manifold minus the union of small balls on such points, the periodic points, like for instance. So it's something like this. So each ball I will draw like this. So you have many balls, and what the lemma says is that for every point P away from outside of these balls, you can connect using using a US path with two legs, the point P with those balls. So any point you can connect like this. Okay, well, this is very easy to do, and the main point is that so in particular you can take r small such that AR, so AR is this, right? AR is connected, still connected, and in particular, since we are outside of the periodic points which have this recurrence, then so you can choose some radius small such that the recurrence of any ball on any point on AR is large. Okay, it's just that because we throw away such point. Okay, this is what says Lemma 2.1. Lemma 2.2 says the following: says that okay, so there is some constant k with the following property. So once again, we take a ball. So for me, this is a ball, and now I will. So this is a ball of radius rho 0 over k on a point P, any point P on AR. And what is this ball? So okay, so for me this is the central direction, and this is the stable, unstable direction. Okay. And the lemma is, well, so P is the center of the ball, and the lemma is very very easy also to do the following. So if you take any 2 points, Q1, Q2, okay, and then if you take the central manifold, it's not central manifold, like center disk, okay, over Q2, but with so this is a center disk with radius rho 0. Recall that k is bigger than 1, so rho 0 is way bigger than rho 0 over k. So this red line crosses, and the lemma says that okay, so you can join Q1 to this red line with using only 2 legs. Okay, this is for any K1, any Q1 and Q2 on the ball. Okay, it's also very easy to do this. This is Lemma 2.2. and finally Lemma 2.3. So it's the following. So now, so we have this k, right? And then let's let k greater than 1, and you take rho 0 very small. And the thing is that so you can find a cover of AR by, so all of these are balls of radius rho 0 over k, like in the previous lemma, on some points qi. And the main thing is that so if you take the center disks on such points, this qi should be py. Okay, but anyway, so if you take the center disks, then they are disjoint, and moreover also the images are disjoint. If you iterate at least one, of course, at least one iterate you take. And the iterate is less than capital J. That is the recurrence that we fix. Okay. So we have this cover of AR, and with that, with those lemmas, so we can prove the or the results. The lemma 2.3 is the most difficult in some sense. It's not too difficult, but anyway, and I will talk about in another video. But let's finish the proof. So okay, so the proof of 1.2 so is the following. So okay, so we have those covers, and of course our disks will be the center disks. Okay, so our family will be this family of disks, which is finite by L. Okay, and the main thing is that, well, so we have the following. So using the lemma, so let's suppose that this is AR, and then suppose that you have BY and BJ that intersects. Okay, and then so you have the center disks over PY, and the main thing is that so any point we can, so a point here, so we can join to this red line by a US path with two legs, and also we can join with another path with at least two legs to the other red line. Okay, so the main thing is that we can join these center disks, but when they intersect, so if BY intersects BJ, then we can join these two disks by a four-legged US path. Okay, and now since AR is connected, then any disk for any Y and J, any disk dy of the point PY, we can find a chain of disks, of distant disks. Sorry, this is DJ. We can find these disks, and then we connected each disk using so from here we use four legs, from here we use four legs, four-legged, and since we have only a finite number L of disks, so we can join dy to dj using at least 4 L legs. Okay, and now it's so, and remember this, that this is on AR. Okay, and now so given P and given Q, so by the first lemma we can join P to one point on AR. So AR, so this is one disk on AR, so I don't know, dy. Q also, we have another disk on another ball on DJ on AR also. So we can join this by another path using two legs, and then as we saw, this we can join by a sequence of modulus disks, right? Mod disk, this to this, using 4L legs. So okay, so we have this accessibility modulo such these central disks, right? Using at least 4L plus 4 legs. Eight legs. Because because I forgot that. So this point here we need to join to the disk, and this point here also we need to join to the disk. So okay, so there are four more legs, and this is done. So this is the proof of the lemma, without talking about this covering lemma, which I will talk about later. Okay.